Hi, good morning and Assalamualaikum. Today we're going to continue with part 2, chapter 11, Dynamic Behavior of Closed Loop Control System. Now, if you can recall, last week we have learned on two problems in process control, which are servo problem and regulator problem, where the servo problem is regarding the set point change and regulator problem is regarding the disturbance change. And if you can recall, we have derived the closed loop transfer function for servo problem, which is y over y set point equal to km gc gv gp over 1 plus gol. Okay, and for regulator problem regarding the disturbance change, so it is your output over disturbance change equal to the transfer function of disturbance over 1 plus GOL. So by now, you need to remember this. You need to memorize this. And you should know how to derive this transfer function as well. Okay. Okay, and you know that GOL is what? Where GOL is a transfer function of open loop, which is equal to GM, GC, GP, GV. So this is GOL. Okay, so last week we have looked at the addition of proportional only controller, where GC equal to KC, right? And we see the response for set point change. Okay, but today we're going to look on the disturbance change. If you have a disturbance change and you using proportional only controller, okay, what happened to the response and to the final value of the response? Okay, now let's take a look on the same example. So this is a liquid level control system, the same example as we have discussed last week. Okay, the control objective is to control the level of this tank by manipulating the flow rate of species 2. So you know that your CV is the level, liquid level, and you know that the manipulated variable is flow rate of species 2, Q2, and the disturbance variable is the flow rate of species 1, Q1. Okay. Okay, so this is the assumption that we use to derive the dynamic model for this system. Okay, so as we have discussed earlier, starting with mass balance and then introducing the deviation variable. Yeah, finally, you can obtain the transfer function for the process GP and the transfer function of the disturbance. So now, for a disturbance change, you need this transfer function of GD, or the transfer function of the disturbance. Alright, for disturbance change, okay, you know that this is a regulator problem. So you know that the output over the disturbance change equal to this equation. If you can recall, we have derived it earlier last week. So now you need to substitute what is your GD and what is your GOL. Okay, we know that GOL is what? GOL is GC, GV, GP, and GM. Okay, we know that only proportional controller is used. So your GC equal to KC. Okay, this is from chapter 8. GC equal to KC if you only use a proportional control. And given in the equation that control valve and the transmitter, okay, the dynamic of control valve and transmitter are negligible, meaning that only the gain are considered, only the gain of control valve and the gain of transmitter are considered. And GP, we know that GP equal to KP over tau S plus 1. And you also derive earlier, you derive GD from mass balance. You know that GD equal to KP over tau S plus 1. So you just substitute and you get this equation where KOL is equal to KC, KV, KM, and KP. Okay, now if you look at this equation, so at this equation, right, it is not in standard form, not standard, not standard. So you need to change it into the standard form like this. So you know that this is a standard form of first order transfer function. So what you need to do is you what? You multiply by tau s plus 1 for both numerator and denominator to remove this term. Okay, so now this equation become Kp over tau s plus 1 plus KOL, right? Okay, now you still this equation not in standard form. So what you need to do is you divide by 1 plus KOL for both numerator and denominator. Now, once you divide by 1 plus KOL, you get this equation. So Kp over 1 plus KOL over tau s over 1 plus KOL plus 1. So you know that your gain is this Kp over 1 plus KOL, and your tau 1 will be equal to tau over 1 plus KOL. Okay, now you have this transfer function of y over d, or the output of level over the disturbance. In this case, your disturbance is flow rate of species 1. So you have this transfer function. Now, if given there is a step change in disturbance, so this is your disturbance of a magnitude m. So bring the Q1, your disturbance, to the right side. Okay, Q1 as. So you can now write the output or your level equal to this time m over s. Okay, this is how you write to indicate there is a step change in disturbance with magnitude m over s. So this is the indication of there is a step change in disturbance with magnitude m. So you multiply with m over s. So now the transfer function become K2m over s times tau 1 s plus 1. Okay, now from this, you can calculate what is the final value. What is the final value? Okay, what is the final value? Well, final value is this, where you have the output or your level, okay, versus time. So over the time, you want to know what is the final value. What is the final value? So that's why, according to final value theorem, Okay, now according to final value theorem that you have learned in chapter 3, okay, with the theorem, limit t approaching infinity is equal to limit s approaching 0 as time the output or the transfer function of the level lah in this case. Okay, so now multiply this equation with s and then substitute with s equal to 0. Okay, so now k2m s tau 1 s plus 1 times s and then substitute s equal to 0. So before that you can remove the s term. Now you substitute this equal to 0. So this one become 0 plus 1 become 1. So the final value is k2m. So you know that the final value is k2m. K2m, right? Okay, from the final value, you can calculate what is the offset. Okay, the offset can be calculated by set point minus the final value. So your set point minus the final value, which is h at infinity. Okay, so for regulator problem, for a disturbance change problem, right? We assume that your set point is equal to 0. So 0 minus final value is k2m, which equal to negative k2m. So you know that negative k2m is your offset. So this is what we have calculated before. The offset equal to set point minus the final value, and the set point equal to 0 because this is a regulator problem. We only consider the disturbance change, right? So 0 minus the final value equal to negative k2m, and substituting the value of k2 where k2 equal to kp over 1 plus kol, so we give the offset equal to negative kpm over 1 plus kol. Okay, so according to this result, okay, for this disturbance change and from last week for set point change, okay, both indicate that the use of proportional only controller will leave an offset, meaning that your offset is not equal to 0. So to eliminate the offset, we need to use a additional control mode, which is the integral control. So we need to integrate the integral mode into the proportional only controller so that this offset can be eliminated, meaning that your offset become 0 lah. So we want the offset to be equal to 0. Okay, so one way to eliminate the error is by using the integral mode together with proportional control, right? So for PI controller, we know that this is the transfer function for PI controller that we have learned in chapter 8 that I asked you to memorize earlier, right? So for a disturbance change, okay, we are interested on the output of a disturbance change. So the same step that we have discussed or we have done earlier, okay, the same step by substituting what is GD and what is GOL. But this time you need to substitute with a new GC transfer function. Okay, this part. This is the transfer function for PI controller. The rest are just same as the previous example lah, right? So you have this equation. Okay, now if you look at this equation, this is not in standard form. So you need to change in the standard form. Right. So if you look at the equation, you want to remove this term. So you need to multiply by tau s plus 1 over tau s plus 1 for both numerator and denominator. Okay, when you multiply by this, right, you get this new equation. Okay, but then the equation is not in standard form as well. Now you need to remove this term. So you need to multiply by tau is over tau is for both numerator and denominator. Okay, so you will have this equation. Okay, so you have this equation now by expanding the term in the denominator, right? So you will get this equation, and then if you notice, you have the same S term, and then you need to gather this S term together, and you get this equation, right? Okay, so if you notice, you have this S squared term, meaning that this is a second order process, but this is not written in standard form because you have KOL here. And we know that for second order, okay, this is the standard form of a second order process, right? So what you can do is now you divide by KOL for both denominator and numerator so that this become 1, right? So dividing with KOL, so this become KP tau I S, but you know KOL is KP, K, C, KV, and KM. So if you notice here, you can remove the KP term, okay, and then the denominator become tau I over KOL plus tau I over KOL times 1 plus KOL S plus 1. Okay, now the equation is in the standard form. Now you can compare these two equations so that you can find the expression of K3 and tau 3 as well as the epsilon value equal to what, right? Okay, now comparing the K3 term, okay, you know that K3 equal to tau I over Kc, Kv, Km, and then comparing this term with tau 3 square, you know that tau 3 square equal to tau I over KOL. So tau 3 equal to the square root of tau I over KOL. And next, comparing the two damping coefficient tau 3 with this term, you know that 2 times the damping coefficient, and tau 3 is this, so you just write the values straight away. So tau I over KOL to the power of half, which is equivalent to the square root of this term, okay, equal to this term tau I KOL 1 plus KOL, right? And then bring the this term 2 and this term to the right side will give you the value of damping coefficient equal to half tau I over KOL 1 plus QL times QL to the power of half over tau to the power of half over tau I to the power of half, right? So now you can simplify the QL term and the tau I term. So 1 minus half equal to half. So now your damping coefficient can be written as half of 1 plus KOL over half minus 1 equal to negative half. So your KOL should be in the denominator. So this is square root of KOL times the square root of tau I over tau. Okay, so to summarize, the addition of PI controller will make the overall closed-loop transfer function become a second-order transfer function, where this is the standard form of second-order transfer function with this value of K3, damping coefficient, and time constant. Okay, now for a unit step change in disturbance, meaning that your Q1 equal to 1 over S. So you know that Q1 is your disturbance, right? Okay, so you substitute Q1 equal to 1 over S into the transfer function, and you get this equation. Okay, now using final value theorem, you find the final value. Okay, so S times H S. So you multiply by S and then substituting S with 0, you get your final value equal 0. If you calculate the offset, where the offset equal to H set point minus H infinity or final value. And you know that for disturbance change for regulator problem, you know that set point is 0. And the final value we calculate just now using final value theorem equal to 0. So now your offset will be equal to 0, which indicate that the addition of integral control mode will eliminate the offset. Okay, similarly, if you use the you use the time domain ht, you substitute t with infinity, t substitute with infinity, so you will also get the same value lah. So your h infinity will be equal to 0. So the addition of integral action eliminate offset for a step change in disturbance. Okay, one important consequence of feedback control is that it can cause oscillatory response. Under certain condition, the oscillation may be undampened or even have a amplitude that increase with time. So in this situation, the closed loop system is said to be unstable. So what is a stable response? So a system is said to be stable if the output response is bounded for all bounded input. Okay, for example, here if you can see the response here, okay, as time increases, okay, the output will also increase, which means that this is an unstable response because it is unbounded, right? Similar to this response, the output increase over time, right? Which is unbounded. never-ending response, keep increase with time. So this response is called unstable. So a stable response should be bounded lah. The output of a stable response must be bounded, meaning that it has upper and lower limits. Now, according to general stability criterion, the feedback control system is stable if and only if all roots of characteristic equation are negative or have negative real parts. Okay, otherwise the system is stable. So now what is the characteristic equation? The characteristic equation is given by 1 plus GOL. So if you have a closed loop transfer function for a servo problem, so you know this is the uh, closed loop transfer function for a servo problem. So the stability is determined by the roots of characteristic equation from the denominator part. And if you can recall, in chapter 6, you learned about what? Poles and zero, right? So poles is in the denominator and zeros is in the numerator. So if you can recall in chapter 6, okay, for a system to be stable, or if you have a positive pole, okay, this is right half plane, this is imaginary part, this is real part. Okay, if your poles are located in the right half plane, meaning that your system, it will result in unstable response. So that's why the roots of characteristic equation must be negative lah in order to have a stable response. So your poles must be within the left half plane in order for a response to become stable. So similarly, for characteristic equation, the roots of characteristic equation should be negative, or else the system is unstable. Okay, let's take a look at this example. Okay, consider a process with GP equal to this equation that is open loop unstable. Okay, if GV equal to GM, which is equal to 1, determine whether the proportional controller can stabilize the closed loop system. Okay, now first we write the characteristic equation. We know that characteristic equation is 1 plus GOL. And we know that GOL is equal to GC, GP, GV, and GM. Given that GV and GM equal to 1, and then GP already given. Now, if a proportional controller is used, meaning that your GC equal to KC. Now, substituting all the values and the transfer function of controller as well as the transfer function of the process, okay, you get this equation. Now, the roots S will be equal to 1 plus 0.2 kc, right? Okay, in order for our system to be stable, okay, according to a general criterion just now, the root must be negative, right? So your S must be less than 0. So this is must be less than 0, meaning that your Kc must be less than -5 in order for a system to be stable. Okay, based on the root stability criterion, okay, all of the coefficient in the characteristic equation must be positive. But if any coefficient is negative or 0, then at least one root of the characteristic equation lies on the right or on the imaginary axis, and the system is unstable. Okay, now for example, if you have this transfer function or this equation for the characteristic equation, for s plus 2s plus 1. Okay, for example, this is your characteristic equation. So all of the coefficient must be positive in order for system to be stable. If one of the coefficient is negative, so meaning that the system is unstable. Okay, next, if all the coefficients are positive, we next construct the Ruth array. So now, okay, if we have 5s3 plus 2s2 plus 2s plus 1 plus kc. Now you can, all the coefficients are positive, okay? So you can next construct the Ruth array. So how to construct? So now you write 5, okay, 5, 2, 2, and 1 plus kc. Right, so that's how you arrange in a Ruth array, right? And next you can calculate, okay, what is B1, C1, B2, and C2. B1 is given by this equation where B1 equal to an minus 1 times an minus 2, okay, minus an times an minus 3 divided by an minus 1. Okay. Next, for B2, okay, B2 can be calculated by an minus 1 times, okay, times an minus 4 minus an times an n minus 5 divided by an minus 1, right? And C1 and C2 can be determined by this equation, right? Okay, a necessary and sufficient condition for all roots of characteristic equation to have negative real part is that all of the element in the left column are positive lah. So in order for a system to be stable, all of the element in the left column of the Ruth array are positive, as we mentioned just now. Okay. Now let's take a look at the example to improve your understanding on this. Okay, next, in this example, you have all the transfer function for controller, control valve, transmitter, process, as well as the disturbance. Now you need to find the value of Kc that make the feedback system become stable. Okay, first you need to substitute all the transfer function, okay, to get the characteristic equation of 1 plus GOL. So you substitute all the transfer function given here. Now expanding and make it equal to 0. So you expand by multiply all the terms, right? And then make it equal to 0. So you can see that all of the coefficient is positive, meaning that the system is stable lah. Next, construct the Ruth array in order to find the value of Kc. Okay, so this is the characteristic equation. Now you need to arrange in the Ruth array. So put 10, 17, 8, and 1 plus Kc. So this is how you arrange in the Ruth array. And then now you need to find the value of B1, C1, and B2. So in order for a system to be stable, all the element in the left column must be positive. So your B1 and C1 must be positive, right? Okay, now according to the equation just now, B1 can be calculated by 17 times 8 minus 10 times 1 plus Kc divided by 17. So rearranging the equation, you get that Kc must be less than 12.6, and then B2 is 0 because there's no element here. And then you can also calculate what is C1, where C1 is equal to B1 times 1 plus KC minus 17 times B2, but B2 here is 0, so minus 0 divided by B1 lah. So now rearranging the equation, you can find that KC must be greater than negative 1. So in order for a system to be stable, your KC must be greater than negative 1 but less than 12.6. Okay, next example 11.11. I want you to try it by yourself and submit to me as your attendance today. So I think that's all for today. Thank you for your attention.